Hey guys, this is Mrs. Harbin, and we are continuing our study of roots and radicals with radical equations. Before we jump into radical equations, let's do a quick review of how we solve just regular equations. You can see this equation x minus 2 equals 5. We know that we want to isolate that variable. We want to get that x all by itself, and right now what that means is we have to undo what's being done to the x. Right now, it's got a negative 2 with it. So to undo a negative 2, we have to add a positive 2. Whatever we do to the left side, we also do to the right side. So we're going to add a positive 2 to the right. Our negative 2 and positive 2 on the left will cancel, and that leaves us with x equals 7. If we plug that back into our original equation of x minus 2 equals 5, we substitute that 7 back in for the x. We get 7 minus 2 equals 5. Or 5 equals 5. That is a true statement. So this should not be too complicated for you. We're just reviewing those steps of how to solve for a variable. Let's take a look at it when it looks a little bit different when we add radicals. Now the steps are still the same. You can see that we have x minus root 2 equals 5 root 2. We want to get the x by itself. We want to isolate this variable term. So we need to undo what's being done to the x. Right now it's got a negative root 2 with it, so we want to add a root 2. Now notice that when we add a root 2, we've reminded ourselves that there's really a coefficient of 1 in front of that root 2. So we're going to add 1 root 2 to the left side. Whatever we do to the left side, we also have to do to the right. On the left, negative 1 root 2 and a positive 1 root 2 cancel each other out. So we're left with x equals, and then on the right-hand side, 5 root 2 plus 1 root 2 equals 6 root 2. Remember that when we have a term that's involving multiplication, like 5x or 5 root 2, that when we add those two terms, we're really just adding the coefficients there. So 5 plus 1 equals 6, and our root 2 stays the same. Let's take a look at another one. We've got y plus 7x equals 4x. And let's say I want to solve this for y. I want to rewrite this equation in terms of y. In order to do that, we need to get the y term by itself. And right now we've got a positive 7x term with it, so we need to get rid of that with a negative 7x. Whatever we do to the left side, we also have to do to the right. On the left side, positive 7x and a negative 7x cancel each other out, leaving us with just our y term, which is what we wanted. And on the right-hand side, 4x minus 7x is negative 3x. Again, we've got a term here that involves multiplication. That's 4 times x and 7 times x. When we add or subtract those, what we're really looking at is just the coefficients. 4 minus 7 gives us negative 3. Okay, let's look at one that's similar, but with roots. We've got y plus root 7 equals 4 root 7. We want to solve for y, so we need to get the y term by itself. Right now the y term has a plus root 7 with it. We want to get rid of that, and the way to get rid of it is using inverse operations. So we're going to subtract root 7 from the left-hand side, and whatever we do on the left, we also have to do on the right to keep our equation balanced. Now notice here we've added that 1 just as a reminder to ourselves that there is a coefficient of 1 in front of that root 7. On the left, positive 7 and negative 7, or positive root 7 and negative root 7 cancel each other out, leaving just our y term. That's what we wanted. And on the right-hand side, 4 root 7 minus 1 root 7 equals 3 root 7. Again, when we have a term that's made up of two things being multiplied, all we are adding or subtracting is just that coefficient. So 4 minus 1 gives us 3 root 7. Let's try one that's a little bit longer here. Now, we've got 4y minus root 3 equals 2y plus root 75. When we're solving for variables, remember we want our variable terms all on one side and everything else on the other side. So we need to get our two y terms on the same side here, and everything else, this and this, on the same side. Now we're going to start with this root 75 and simplify that. You can see we've broken it down into the factors of 3 and 25, which we could write as square root of 3 times the square root of 25. And I know square root of 25, that's a perfect square, so I've got square root of 3 times 5, or how it's written here, 5 times the square root of 3. All right, once we have that simplified, we can start moving our terms around so that we have all of our y terms on one side and everything else on the left-hand side. I want to keep my y term over here on the left-hand side, so I'm going to get rid of this negative root 3. The way I get rid of a negative root 3 is with a positive root 3. So you can see I've added plus root 3 to the left side. Whatever I do to the left side, I also have to do to the right-hand side. My negative root 3 and positive root 3 cancel, leaving me 4y on the left, which is what I wanted. And on the right, I still have my 2y, and 5 root 3 plus 1 more root 3 gives me 6 root 3. Now, I don't want this y term on the right, this 2y. I want to move that to the left. I want to get rid of this 2y on the right. So to get rid of a positive 2y, I add a negative 2y. Whatever I do to the right, I also have to do to the left. You can see that here. On the right-hand side, my 2y and positive 2y will cancel out. And on the left, I have 4y minus 2y, leaving me with just 2y. So I now have 2y equals 6 root 3. Now that my y term is all by itself, I want to further separate this and get just the y by itself. Right now, y is being multiplied by 2, and I know to undo multiplication, I have to divide by 2. So I'm going to divide this side by 2 on the left, and whatever I do to the left, I also have to do to the right. So 2y divided by 2 is just 1y, which we often just write y. And on the right, 6 root 3 divided by 2, I'm just going to look at the coefficients here. 6 divided by 2. And 6 divided by 2 is 3, so I'm left with 3 root 3. Y equals 3 root 3. All right, so that's just a quick review of how to solve for a variable. We looked at it using just variables and whole numbers or integers, and then we just went through a couple of examples and looked at how the steps are exactly the same even when you're using roots or radicals. So let's take a look at what we are doing today. Our objective for today is that you, the student, will solve simple radical equations. Now let's define that. A radical equation is an equation that contains a variable in a radicand. What we saw just a second ago in our example, the variable was never in the radicand. So that doesn't count as a radical equation. It's an equation with radical expressions. But radical equations have the actual unknown in the radicand. Let's see what this looks like. Take, for example, the square root of x equals 10. You can see that this is a radical equation because we have a variable, x, in the radicand. So the steps to do this are very similar to what we looked at before. We want to undo what's being done to the x. Well, what's being done to the x? Hopefully you said it's having its root taken. And the way to undo a root, the inverse operation of taking roots, is squaring. So the first thing we want to do is square that left-hand side so that it will get rid of the root symbol. But whatever we do to the left, we also have to do to the right. When we square our root x, we get just x because the square root symbol and the squaring, they are inverse operations. They undo each other. And on the right-hand side, 10 squared equals 100. The solution checks in the original equation if we plug it back in. So we're going to go right back up here and write square root of x equals 10. We're going to plug in what we said x was, square root of 100, substitute that in, equals 10. And we do know that the square root of 100 is 10, 10 equals 10, so that checks out. We do need to make sure that we check our solution every time in the original equation. Solutions must be checked in the original equation because you may get a solution that may not actually work with the original equation. Solutions that do not make the original equation true are invalid and are called extraneous. Extraneous solutions. So you're going to see when we're going through our steps today that we're always going to check our solution. We do need to check everyone to make sure we don't have any extraneous solutions. When solving radical equations, these are the steps we're going to follow. First, we're going to isolate the radical on one side of the equation. Just like in our simple equations we saw at the beginning here, we isolated the variable term. Now we're going to isolate that radical term. After we have done that, we are going to square both sides of the equation. Remember that squaring is the inverse operation of taking roots, so we want to square both sides to get rid of that root. After we've squared both sides, we will then solve the resulting equation. by solving for the variable, isolating the variable, following all the steps like we did in our review at the beginning of this lesson. Finally, we will check any solutions in the original equation to make sure none of our solutions are extraneous. Let's put those steps into practice by solving this one together. 10 plus the square root of 10m minus 1 equals 13. Our first step, we said, is to isolate the radical. And the radical is everything under that root symbol. Make sure you get everything under that root symbol. It's not just the 10 or the 10m, it's the 10m minus 1. We want to get that by itself, which means we need to get rid of this 10. And the way that we get rid of a positive 10 is a negative 10. So we're going to add negative 10 to the left. And whatever we do to the left, we also have to do to the right. So our 10 and a negative 10 will cancel each other out on the left. And on the right, we have 13 minus 10 equals 3. Once we've isolated the variable, our second step was to square both sides. Squaring gets rid of square roots. They are inverse operations. So let's square both sides here. And when we do square both sides, we get just our radicand here, 10m minus 1, because the squaring and the square root cancel each other out. And then 3 squared equals 9. We'll then solve the resulting equation. We want to get the variable term by itself. And right now it has a negative 1 with it. The way that we get rid of a negative 1 is with a positive 1. So we'll put a positive 1 on the left, but whatever we do to the left, we have to do to the right. That leaves us with 10m equals 10. Now that we have the variable term by itself, we want to further isolate the variable and get it all by itself. Right now it's being multiplied by 10, and the way that we undo multiplication is division. So we're going to divide both sides by 10. And when we divide both sides by 10, what we get is that m equals 1. We then need to go back into the original answer here and check our solution to make sure that it does work. So 10 plus 10m minus 1 equals 13. Sorry for my messy handwriting there. We'll plug in that 1, 10 plus 10 times 1. 10 times positive 1 there, minus 1 equals 13, which gives us 10 plus the square root of 10 minus 1 equals 13. Simplify that further. 10 plus the square root of 9 equals 13. And 10 plus the square root of 9, which is 10 plus 3, equals 13. And we end up with 13 equals 13. That is a true solution. It was not extraneous. So we do need to make sure that we check every solution to make sure they're not extraneous. Okay, try this one on your own, pause the video, and then come back and see if you were able to do this independently. All right, the first thing we want to do is isolate the radical. It's already been isolated. Step 2 is square both sides, and when we do that, we get 2x plus 5 squared equals 8x squared, or 2x plus 5, since the square and the square root cancel each other, equals 64. 8 squared is 64. We'll then solve the resulting equation. Subtracting 5 from both sides, we get 2x equals 59. And we need to further isolate the x by dividing both sides by 2. X equals 59 over 2. If we were to plug that back in, we would find that that solution does work. It is not an extraneous solution. All right, let's solve this one. Root 39. Our square root of 3n plus 12 equals square root of n plus 8. Now we have two radicals here. So we just want to work with one at a time. So if they were on the same side, we would want to move one so that just one was isolated. So we can solve one at a time. But we do have just one on a side. So we can go ahead and go to step 2, which is square both sides. Well, you're going to see when we square both sides, what's being undone is the square root on both sides, which leaves us with 3n plus 12 equals n plus 8. We will then solve the resulting equation. I'm going to subtract n from my left here so that it's my n variables on the right, and subtract 12 from the left so that just my numbers are on the right, and I get 2n equals negative 4 when I do both of those steps. I'll then divide both sides by 2 and get n equals negative 2. If we plug that back in, we'll see that it works. It is not an extraneous solution. All right, today we solved simple radical equations by following these steps. Isolate the variable, square both sides, solve the resulting equation, and Plug it back in to check your work. Isolate, square, solve, and plug in to check your work. If you have any questions, ask me next.